Bismillahirrahmanirrahim. Assalamualaikum and a very good afternoon. Okay, today we are going to discuss the last part of the fourth chapter, which is the circuit analysis using Laplace transform. Okay, to begin with, let's look at initial value theorem. So initial value theorem is used to relate frequency domain expression to time domain behavior as time approaches zero. Okay, so relation between the time domain and frequency domain in which the time approaches zero. Okay, so this is the function in time domain. So when t approaching zero, so to solve this initial condition, so in frequency domain we use Laplace transform in which the limit as fs, so you have ft here, so in Laplace transform it is fs and the equation is multiplied with s, and s in this case approaches infinity. Okay, so initial condition or initial value theorem happened when your function in time domain with t approaching zero, but in s domain the s approaching infinity. Okay, so the initial value theorem can be solved by using this particular equation. This is the general equation for initial value theorem. Okay, let's look at an example on initial value theorem. So given a function of ft equal to the following equation, so solve the initial value of t. So in this case, we need to use the initial value theorem in which it is limit when t approaches zero. So initial t approaches zero, your equation, so ft. So in s domain, it is limit when s approaching infinity, and then it is s f s. Okay, so in this case we have the ft, so we need to find the Laplace transform of ft. So again, as usual, you need to refer to Laplace transform table to get the Laplace transform for this particular equation. So you can find different components, so you need to refer to different equation from the Laplace transform table. For example, we have 3t squared here. So 3, from the basic equation, we know that when we have t and ut, so the Laplace transform will be n factorial divided by s to the power of n plus 1. So in this case, to the power of 2, your n is 2. So t to the power of 2, so your n is 2 factorial divided by s2 plus 1. So it is 2 factorial divided by 2 plus 1 s to the power of 3. Go for the second component, we have 4t to the power of 1, so it's 1 factorial. For this one, it is 4 multiplied with 1 factorial divided by s, your n is 1 plus 1 for the second component. And then for the third component, it's just 3. So 3 ut, so if you have ut, so the Laplace transform will be 1 over s. So in this case, you have 3 ut, so it is 3 over s. Okay, so you have the fs equation. And then to solve for the initial value theorem using Laplace transform, so this is the initial value theorem. So now you need to multiply the s with your fs. Okay, so s multiplied with fs, so you can simplify the equation. So s, this one become to the power of 2, this one become to the power of 1, and then 3 over s, multiply with s, you get 3. Okay, so from this equation, now you apply s approaching 0. What happened when s equal to, s approaching infinity? So what happened when you have s approaching infinity? So we put s as infinity. So s infinity, 6 divided by something very big. So it will be almost 0. So here also 0. So the initial value will be 3, or we can say 3 unit. Okay, next is the final value theorem. Okay, it is basically more or less the same as the initial value theorem. It is a theorem that used to relate frequency domain expression to time domain behavior as time approaching infinity. Okay, if you recap back the initial value theorem, it is happening when t approaches 0. But in final value theorem, the t approaching infinity, but SFS with s approaching 0. Okay, so for initial value theorem, we know that it is limit t approaching 0 of ft and the s approaching infinity as fs. But in final value theorem, you have t approaching final value theorem. So you have the t approaching infinity. When it is final, meaning that t approaching the last condition, the last value, it is infinity of ft, and in s domain it is now s approaching 0 as fs. Okay, so initial mean earlier, so t approaching 0. So final, t approaching the last point, infinity, but the s approaching 0 in final value theorem and s approaching infinity for the initial value theorem. Okay, let's look at this example. Given gs equal to the following equation. Okay, the following equation, calculate the final value of gt. Okay, so we need to apply final value theorem. So again, please remember the final value theorem fundamental equation. So it's limit t approaching, so final approaching the last point, infinity of ft, and then the in s domain is s when here is approaching infinity, so here approaching 0, and then s fs. Okay, so in this case we use gs, so in time domain it is gt. Okay, so final value theorem for this particular equation. So it is limit t approaching infinity of gt, and here is limit s approaching 0 of s multiplied with gs. So now we have you have the gs given to you, so you just need to multiply your gs with s. Okay, so s with your the given gs, 2s plus 2 divided by s plus 3, s plus 4. Okay, so simplify the equation. So don't forget, in this case, s approaching 0. So you can replace all s with 0. Okay, so here s is 0, here s is 0, and another one is 0. So now the equation becomes 2 multiplied with 2 divided by 3 multiplied with 4. So it's 4 over 12, or 1 over 3 unit for the final value of this particular equation. Okay, let's look at this example. So please try this out. The answer is given to you at the bottom underneath the question. So please try this out. Okay, the question asks you to solve for initial and final value of xt. So don't forget the initial value theorem. So you have limit initial means earlier, so t approaching 0 of equation, so xt in this case. So in s domain it is when t approaching 0, s approaching infinity, so s x s. And for final value theorem, it is final value theorem. So final means last point, so t now approaching infinity, and that of xt, so in s domain s approaching 0 of sxs. Don't forget to multiply with s This is common mistakes by students when they forgot to multiply the S domain equation with S. They just solve for XS. So don't forget this theorem. Okay, so try this out. You should get the answer as shown underneath the equation, in the underneath the question. Okay, next let's step in the final part of Laplace transform, so which is the application of Laplace transform in circuit analysis. So there, as usual, there are three main passive components in electrical circuit: inductor, capacitor, and resistor. So the differential equation of Laplace transform is used to solve the circuit that is transformed into S domain. Okay, let's look at the circuit analysis when we have a resistor in your circuit. So this is your circuit in time domain when you have a resistor, and when you transform the time domain circuit into S domain circuit, so you need to transform all components, including the source, the current, and also the passive elements, into S domain. So R in S domain will appear as similar as R in T domain. Okay, so in terms of mathematical expression, so Vt, this is the equation in time domain. So as usual, from your circuit analysis or circuit and system, Vt equal to Rit. And when you perform the analysis using Laplace transform, so you need to convert each time domain function into Laplace or S domain function. So in this case, your Vs equal to Ris. Okay, next, when we have an inductor in your circuit, so this is the time domain representation of a circuit, including a single inductor in that circuit. So as earlier, so you need to convert the circuit into S domain function. So this may appear as a series of an inductor with additional source that dependent on the initial condition, okay, the initial current, or you can also represent the circuit by having the inductor in parallel to the current source. Okay, so in this case, the I become Is, Vt become Vs, and the L become SL with additional source of L negative 0. So if there's no initial condition, so I negative 0 will be 0. So or in the parallel representation, so again the L in time domain will become SL in S domain, and the initial state or additional current source of I naught divided by S. So in terms of mathematical representation, so in time domain, Vt equal to L di over dt. So if convert this into S domain, okay, so L di dt, so you have differential equation in time domain. So when you convert into S domain, so you need to perform conversion of differential equation. So di to the power of 1, so you have single s, sis minus I naught. So I naught is the initial current, and this equation can be further expanded into this form. So this is in terms of Vs, or you can also represent the equation in terms of Is. So from this equation you can get the Is equation for an inductor in a circuit. Okay, next let's consider when you have a capacitor inside a circuit. So this is the time domain representation of the circuit. So you need to convert the circuit into S domain function. So either you can use series connection, or you can also use parallel connection. So this capacitor will be represented as a series of capacitor with additional voltage source, so that dependent on the initial condition, initial voltage value, and also the C become 1 over SC, while in parallel connection C will be 1 over SC in S domain, and additional current source of C, V0. Okay, so in terms of mathematical representation, so IT equal to C dVt over dt. So again, you have differential equation in time domain, so you can perform conversion in Laplace transform. So SVS minus V0, and you can further expand the equation into this form. So from here you can get the Vs equation, which is equal to the following equation. Okay, this slide summarizes the method of solving circuit analysis using Laplace transform. So the first step, you need to determine the initial condition, either initial current or initial voltage, by using your knowledge in circuit theory or circuit and system. So then you need to convert all components, including the source, the resistor, inductor, and capacitor, into S-domain function, including its initial voltage or current. And then the second step, you need to transform the given time domain circuit into S-domain function, and you need to sketch the S-domain circuit diagram. So usually that's marked for the sketching. Okay, so in order to solve circuit using Laplace transform, so it will be recommended to sketch or include a diagram of S-domain circuit after conversion from time domain. So next you need to solve the S-domain circuit, okay, depending on the question. And lastly, you need to perform the inverse Laplace transform to get the time domain function. Okay, and let's look at the first example, a simple example on circuit analysis using S-domain function. So find IT when the switch S is closed at t larger than 0, with assumption that the value of initial current equal to 5 ampere. Okay, so again, you need to remember the first step. So the initial current is given, so you just need to convert the given circuit into S-domain equivalent circuit. Okay, so in order to solve this, to find IT using Laplace transform analysis, so first we need to convert the given circuit into S-domain function. So we can use this one. So in this case, the L will become SL. So in this case, the L equal to 2. So it becomes 2S. And then Li naught, so as stated in the question, so I naught equal to 5 ampere. Therefore, Li naught, so your L is 2 multiplied with I naught 5. So it is equal to 10. Okay, and then you have the resistor, so the R stay at it as it is in S domain, and then you need to convert the Vt equal to 3 Ut into Vs. So in this case, when you have Ut, it is 1 over S. Okay, so this is your circuit. So the source is 3 over S, and then you have the series of inductor with additional voltage source, and then you have the resistor. Then you can solve for RS. So you need to represent the Laplace transform equivalent circuit, and that's mark allocated for your sketching. Okay, so then you need to perform further analysis using mathematical expression. So in this case, you can write the loop equation, so you can find the IS. So in this case, you need to perform as usual the partial fraction expansion to determine what is the a and b, and then you need to write the equation again after you have calculated what is a and b, and finally you need to perform inverse Laplace transform to get it as the final answer. Okay, with that I end the first part, so I'll be providing you with more examples in the next presentation. Thank you.